swing equation, right? And we calculate the slide of swing equation, and also show you some mathematical problems that can come from the swing equation. Now, from today, actually, we will start the new topic that is called the economic load dispatch. Okay, is the economic load dispatch. Shortly, it is called as ELD. It's called the ELD. So, as you know that for this course there will be no quizzes, right? So, I will give you one complex engineering problem as an assignment, which will carry 45 marks. So, I am on the stage of designing the complex engineering problem. That problem will be actually based on the economic load dispatch. Okay. That's why I want to complete this topic this slide before mid. Also in the midterm exam this topic will be included. Okay. So then once this topic will be completed, then we will get the idea how to solve the complex engineering problem. Okay. Everyone is understood? So what is actually economic load dispatch? So before going into the game, you can actually give one example. Okay, so let's say we have 3 generators: generator 1, generator 2, and generator 3. Okay. These 3 generators are connected to a power system network, and let's say this power system network is delivering some loads to the customers. Okay. This is load 1, load 2, and load 3. Let's say at a certain time instant, the load 1 has a demand of 100 megawatt, load 2 has a demand of 50 megawatt, and load 3 has a demand of 20 megawatt. So combinedly we have 170 megawatt demand, okay, from the customer end. Now, let's say you are a power system owner, you are sitting at this side, the generation end. Okay. So, what will be your first target? You are observing that the load demand is 170 megawatt. Okay. So, in response to this, what will be your first target? Your first target will be to generate amount of power, right, from the generation end. This is your first target, and summation of all power generation, okay, from all these 3 generators will be at least equal to the summation of all load demand, right? And now obviously you can consider the power loss, because there are some transmission lines, so within this some transmission losses will be there, right? So you can add those things. If you want to add the transmission losses, you have to add that thing in the right side, right? So it will be P loss. So considering the P loss, the summation of all summation of generations of all generators will be equal to the summation of load demand plus the loss. Then what will be the next point? So obviously you can generate infinite amount of power from each generator, right? There is some capacity, or there is some maximum limit for generation from each generator. Whenever the manufacturers produce or manufacture the generators, they actually write the maximum capacity on the body of the generator, right? On the nameplate. So let's say you have the PG1 max for the generator 1, you have the PG2 max, PG3 max, right? Then whatever power you want to generate from any particular generating unit, that's why I am making some indexing here. That is, the I means it can be 1, 2 or 3. Okay. So the generation from any particular generator should be less than equal to this maximum limit, right? So it will be the PGI max. So there should be some upper bound for generation, as well as there are some lower bounds, right? Because you know that there is some Pg1 min, Pg2 min like this. Okay. So obviously this generation Pgi should be higher than or at least equal to the Pgi min, right? So this Pgi max, it can easily be understandable that yes, there should be some maximum capacity because one generator can generate infinite amount of power, right? So that's why there should have some maximum capacity. But can anyone say why there is some minimum capacity? What is the point of this thing?
To meet the cost, like labor cost and.
Yeah, that can be one point. So he is actually saying that if you turn on one generator, so rather producing only 1 megawatt or 2 megawatt, you can produce at least some amount of power. Let's say if the minimum amount of power is 50 megawatt. So once you turn on this generator, at least generate this 50 megawatt of power. Otherwise, your all other cost will be higher, right? Or it will not be the efficient system. That can be one answer. Actually, the answer is a bit complex because there are many other terms. Okay. So one term is that whenever you are solving this network, okay, and if you solve the load flow, okay, you will get the power flow directions, right? Let's say after solving the load flow, you are getting this direction of power to this generator. That means that this generator is taking power rather than delivering power, right? Now will this machine work as generator or motor? It will work as motor, right? So to prevent this type of phenomena, that to ensure that your generator is actually working as a generator, that's why you need some minimum amount of power generation from this generator. Okay. Now obviously these values will be given within the generator networks. Okay. Now we have understood that somehow we have to generate the power from all generators such that it can meet the load demand plus the transmission losses. Okay. So how can we actually generate the power? Okay. How can we generate the power? We need the fuel, right? So if you think as a power system owner, you need to buy or you need to import the fuel, right? And for that you need money, right? So that means there is some economics related to this power system operation, right? And that economic term of power system operation is called as economic load dispatch. Okay. And from that term, we can say that this is the economic load dispatch or ELD. Now, this ELD actually it can be represented as optimization problem. Okay. Optimization problems. Okay. That means we want to optimize some parameters. Okay. There are a few steps to solve the optimization problems. The first step is that you have to define the objective function. Let's say for this example, and depending on your objective function, your optimization problem can be of minimization type problem or maximization type problem. Okay. Let's say for this example, your objective function is fuel cost. So what should be your target? To minimize the fuel cost or to maximize the fuel cost? To minimize the fuel cost, obviously, right? So if you take this fuel cost as your objective function, then obviously it will be a minimization type problem. Now the same problem can be treated as maximization problem. How? Let's take the profit, okay, as the objective function. Okay. So if you take this variable as your objective function, then you want this profit to be maximized, right? So at that time, it will be a maximization type problem. Okay. So the same problem can be viewed as minimization problem or maximization problem. Now the next step is to define the constraints. What is constraints? It is actually nothing but the limitations. That means if you do not have any limitations or constraints, okay, or if you do not have any boundary, okay, then your optimization problem will be an unbounded one. How? Let's say for this problem, okay, your objective function is fuel cost. So it is a minimization type problem, right? So what is the minimum value of fuel cost? It will be 0, right? So if your fuel cost is 0, what will be the PG1, PG2 and PG3? It will also be 0, right? Because if you do not invest any money on fuel cost, there will be no fuel. So without fuel, there will be no generation, right? So these 3 will be 0 megawatt. Okay. Now with this set of solution, can you fulfill the load demand? No, right? So this is not a valid solution, right? So that's why you have to define your constraint. Okay. So this constraint can be your equality type constraint or inequality type constraint. Okay. So what is equality type constraint? Here, the first point. What is it? It is actually the summation of power generation should be equal to the summation of load demand plus loss, right? So whenever you will have this equality type constraint, then you can easily understand that this can be your valid solution, right? Right? Because let's say here your demand is 170 megawatt. So somehow from these 3 values, you should get the 170 megawatt generation, right? So if you include this equality type constraint, then actually this so this type of solution set will be vanished from your solution, right? Then what is the example of inequality type constraint? The second one. Look, this is the inequality type constraint. Okay, your generation from any particular generating unit should be under these 2 limits: the minimum generation and the maximum generation. That means, let's say you are getting this type of solution. You are getting 170 megawatt from here and 0 from here, 0 from here, right? Let's say for this solution, you are getting the minimum fuel cost. Okay. Now, with this solution set, you can fulfill the load demand, right? Because here the total generation is 170. Also, your load demand is 170. But let's say your PG1 max was, let's say, 100 megawatt. Okay. Now, can you produce 170 megawatt from this generator one? Obviously, right? So if you incorporate this inequality type constraint in your problem, then obviously this solution set will also be vanished, right? So that's why to actually get the optimized and the practical or the feasible solution, you need to incorporate all of the constraints that are related to the problems, right? So have you understood this thing? If you have any confusion, you can ask. Because I am just giving you the concrete essence of the economic load discussed with just one example. Gradually, we will see all of these things in the later slides. Okay. So. So these 2 are the steps for our optimization problems. Okay. So after defining these 2, we can solve the optimization problems. Okay. Now let's come to our main point. What is actually the economic load distress? Okay. Now using this explanation that I have already given you can easily say that our ELD or the economic load distress tells us actually how to distribute the load demand across all available generators so that the fuel cost is minimum, right? So your goal is to minimize the fuel cost and your target is to meet the load demand, right? And that means I can say it another way that the goal of the ELT is to minimize the fuel cost or minimize the total operational cost while satisfying or while fulfilling all the constraints associated with the problems, right? So why actually I am telling about the fuel cost? Because it is more practical to say about the operational cost, right? Operational cost actually encompasses the fuel cost, the land cost, also the labor cost, all other costs, maintenance cost, right? This type of things. But for the initial stage, we will only consider the fuel cost, okay? So that we can understand the basic of the ELT. But obviously the other cost or the other variables could come, but that will make our system or make our calculation a bit more complex. Okay, that's why in order to in this slide or in this discussion in this ELT, we will only consider about the fuel cost. Okay. So this is obviously the mathematical problem, right? So somehow we have to formulate all the expression like fuel cost, objective function, constraints into mathematically, right? So that's why we need to study the generator cost curves. Okay. So there are 4 types of generator cost curve: input-output curve, fuel cost curve, heat rate curve, and incremental cost curve. Now we will explain these 4 curves separately. So what is the input-output curve? Actually, what is the input and output of our system? Here we have the generator. So at the output side, we will get the PG, right? The electric power output. So obviously this is our output. There is no doubt that this is the output, right? Then what is the input? If we go back to this side, okay, so before generator we have the turbine, right? It can be gas turbine or steam turbine. So turbine has some blades, right? So that blades will be rotating and the generator shaft is connected to the turbine. So whenever the turbine rotates, generator will also rotate. And generator actually converts that rotational energy into the electrical energy at the output side, right? That is actually basic mechanism. Then before this turbine, how actually this turbine runs? We need some fuel right here. So this fuel is our initial point. So we need some fuel, we need to burn them. From the burning we get some heat. Then heat is actually used to rotate the turbine, right? You understand this thing. Obviously in the intermediate step there is another thing, that is the boiler, okay? That is actually the boiler. So inside the boiler you will have the water or gas depending on the turbine. If the turbine is steam turbine, then it will be the water. Okay, if then it is the gas turbine, it will be inside the boiler. The component or the material will be the gas. Okay. So using this fuel, you will generate the heat. That heat will be used to boil up this water to produce the steam, right? That steam will be used to rotate the turbine blades, and those turbine blades are connected to the generator via a shaft, which will cause the rotation in the generator, and finally we get the electric power output. Okay, that is actually the basic mechanism. Actually, you need to know this type of things because whenever you will go to the job market, you will face the interview. This type of questions may come, right? And how actually the electricity is produced. Okay, you should know the background, right? So this fuel, you can say it as this is our input. Okay. So in the input-output curve, it shows the amount of heat input energy in MBTU. BTU is the British thermal unit. M stands for mega. Okay. So mega British thermal unit required per hour. So this is important. This is the heat input energy per hour as a function of generator's output megawatt. Okay. So in the x-axis we have the output, that is the generator power in megawatt, and in the y-axis we have the amount of heat input energy per hour, that is in MBTU per hour, right? Now this is x-axis, this is y-axis, right? can anyone say which one is the independent axis and which one is the independent variable? Actually, x-axis is the independent axis, right? This y-axis is the dependent axis. So here you can see that this generator power is actually leveled across the x-axis, right? So and it is in the y-axis. So it means that this generator power is the independent thing and this is the dependent thing, right? But you can say the opposite thing, right? These are actually, this should be the independent and this generator power should be dependent upon that thing, right? That should be the ideal case. But here actually we are thinking this from the opposite side. Let's say we have some load given here, right? We can control the fuel. This is in our hand. But can we control the load given? No, right? Let's say it is fixed at 170 megawatt, right? We know this information. So based on this information, this is fixed. Our output is fixed. That's why this should be the independent thing. Okay. And depending on this fixed output, how much heat or how much fuel we need per hour, that is given across this y-axis. So that will be our dependent variable. Okay. Any question up to now?
Both are getting the
Actually, this is written as wrong. It will be actually the heat input energy per hour. Okay, heat input energy per hour. Actually, this should be in the caption. Okay, this figure is the actually input output curve, and this y-axis labeling should be the heat input energy per hour. Now you can see that whenever the generator power in megawatt is 0, you are getting some amount of heat needed, right? Can you say why we are getting this type of things? Why this curve is not starting from 0? Yeah, exactly. Because we have some preheating steps, right? So here there is some fuel. Using this fuel we are producing heat. So this heat is used to produce the steam, right, from the water. So in first few cycles, we need the heat to produce the steam, right? So at that time, some fuel will be wasted, right? And that fuel will not be used to generate the effective power, because yet actually whenever there is no steam or if the turbine is not rotating, we are not getting the effective power, right? So to actually rotate the turbine or to actually start the system, in the beforehand we need some extra fuel to actually boil up the water to generate the steam. Okay. So from that concept, we are getting some non-zero fuel cost or non-zero heat energy required at the initial stage, at the preheating stage. Now the next curve is the fuel cost curve. What is the fuel cost curve? It actually specifies the cost of fuel in dollar unit. Okay, or it can be in any other currency. If you think about our country, then it will be BDT. Okay, so the cost of fuel in dollar unit used per hour. Okay, so this is the fuel cost used per hour by the generating unit as a function of the unit's megawatt output. So here the x-axis unit variable is set. The generator power megawatt, but in the y-axis we have here the fuel cost, and the unit is dollar per hour. And previously we had the heat input energy in MBTU per hour, right? And the x-axis are same for both curves. Obviously, at the initial stage there will be some non-zero fuel cost, right? To actually start up our system. Now the heat rate curve. What is the heat rate curve? Actually, this heat rate curve is the input-output curve scaled by megawatt. Okay. What is the meaning of this? That means that you will take this input-output curve. Okay. You will take this input-output curve. Then actually you will divide it by megawatt or by the generation. Okay. Then actually you will get this curve. That's why here in the y-axis it is written as heat rate and the unit is MBTU per megawatt hour. But previously it was MBTU per hour, right? As you are dividing the input output curve by megawatt or by the total generation. That's why the unit is now MBTU per megawatt power. Okay. Then you will get this heat rate curve. But you can ask that what is the significance of the heat rate curve. Okay. Now let's talk about the difference between this heat rate curve and this input output curve. Okay. So from this input output curve, it will give you the direct relationship between the megawatt and the heat input energy. Let's say you want 300 megawatt, right? So you go across this line, you will get this point on the curve, then go across the y-axis. Let's say this value is 2800 MBTU per hour, right? That means to generate 300 megawatt power, you need this amount of heat energy, heat input energy per hour, right? That is the information that you actually get directly from this curve. But the heat rate curve tells you the different thing. What is that thing? Here actually this is scaled by megawatt. That means it will give you some more information like this. So let's say this is 100 megawatt, right? And let's say the next point is 101 megawatt. Okay. So to produce the additional 1 megawatt power, how much additional heat input energy is required? Okay, that information you will get from this thing. Okay, that information actually you will get from this part. Okay, so that's why it will give you the information that to produce additional 1 megawatt power, how much additional heat energy you will need per hour. Okay, that information you will get from this curve. And actually this curve is based on the generator efficiency. Okay. What does it mean? It means that let's say for the first few cycles, whenever you are turning on your generators, in the first few cycles your generator efficiency will be low. Why? Because now your turbine is just getting the speed, or the generator is just started to work, right? So in the first few cycles the efficiency will be low. So efficiency low means to produce additional 1 megawatt power, you need more additional heat input energy, right? So that you can see from here. Look, these are the first few cycles, right? So if you go from here to here in the reverse side, in the first few cycles, you can see that the slope is positive, right? That means to produce additional 1 megawatt power in the first few cycles, the additional heat rate or heat required heat rate is higher, right? Because the efficiency is low for the first few stages. But whenever the turbine is now rotating at rated speed, or now all the equipments are actually working finely, at that time the generator efficiency will be high. Okay, and at that time you will see that this is almost a flat line, right? Have you understood this thing? Flat line means that to generate 1 megawatt additional power, you need uniform increase of heat input energy, right? Yeah, not actually. Here you can see that it is means that here the difference is 0. Difference 0 means to produce actually additional 1 megawatt power, you do not need additional power. Additional means obviously you need additional heat, but here let's say from 100 to 101, okay, you need the additional heat energy of 2 MBT. That's okay. For 101 to 102, you need 4 because this is the initial step, right? It is not uniform. But whenever you will go to the uniform stage, this rate will be same. That's why here the line is the flat line. Okay. Here it will be for to actually generate the additional 1 megawatt power. Here the rate will be uniform. Okay. That is actually the heat rate curve. Then the last curve is the incremental or the marginal fuel cost curve. Okay. So what is the incremental or marginal fuel cost curve? So it can be found by differentiating the fuel cost curve. Okay. So you will see the fuel cost curve here. So this is the fuel cost in dollar per hour. with respect to the generator power in megawatt. If you differentiate this curve with respect to the megawatt or with respect to the generator power, then you will get this incremental or marginal fuel cost curve. Okay, that means let's say your fuel cost curve is represented by C. So this is your fuel cost curve. Fuel cost curve. Okay. So how can we get the incremental cost curve? Let's say this is the incremental cost curve IC. Okay. It will simply is differentiation of C over P, right? Okay. So then you will get the incremental cost curve, and obviously the unit is here dollar per megawatt hour. Okay. Now in summary, we can say that there are 4 types of curve. The first curve, that is the input output curve, and the third curve, the heat rate curve, these two are related, right? And the fuel cost curve and incremental cost curve are related, right? This heat rate curve is found by scaling up this input output curve with respect to the megawatt, and then the incremental cost curve is found by differentiating the fuel cost curve with respect to the megawatt of the generated power, right? Now we need to formulate the cost curve mathematically. Okay. Now let's formulate the cost curve mathematically. So it is said that generator cost curves are usually not smooth. However, the curves can usually be adequately approximated using piecewise smooth functions. Okay. So that means that this cost curve, let's say C of the cost curve, actually there is no fixed formulation for this cost curve. So in different literatures or in different research papers, you will see different cost curves. Okay. But there are 2 representations for cost curves that actually predominate in the literatures. Okay. The first type is that some literatures actually formulated the cost curves using quadratic or cubic functions. Okay. And obviously this type of relationship is the non-linear relationship, right? So it can be quadratic or cubic. So what is the quadratic means? In that case, it will be, let's say, C of the cost curve, it will be simply a P square. P means the generated power. Obviously, the cost curve will be the function of generated power, right? Then BP plus C, this is the quadratic function. And if you think about the cubic function, it will be AP cube plus PP square plus CP plus D. Okay. So this is first type. And in other literatures, actually some researchers formulated the cost curve using the piecewise linear functions. Okay. So are you familiar with this term, piecewise linear function? Can you say what is actually the piecewise term?
Depending on the portion it is entirely it is not.
Exactly. So let's say this is a non-linear curve, right? So if you think about the entire curve, it is actually the non-linear curve. But you can actually make pieces into the few zones, right? Let's say this is one zone, this is another zone, this is another zone, right? So in this zone, you can approximate this non-linear curve into a straight line, right? In this curve, there will be another straight line. Here, there will be another straight line, right? So we are actually making pieces of some straight lines, right, from this non-linear curve. And this type of representation is called the piecewise linear function, or piecewise linear representation. Okay. So because dealing with these quadratic or cubic functions, sometimes it seems difficult to solve the problem. Okay. That's why if you somehow represent the nonlinear relationship into the piecewise relationship using these things, then your calculation will be easier. That's why in some literatures, actually the researchers used these piecewise linear functions. Okay. And obviously in other literatures, there are different cost curves. Okay. There are different cost curves. Now at this point, I want to give you one information, that is that in your complex engineering problem, which will be based on this economic load dispatch, and so your first task will be to study some research papers or data research, okay, and then you have to take one cost function, okay. Obviously all the groups will not take the same cost function, okay. Maybe one group can take the cubic function, another one we can take piecewise linear function like this. Okay. And in this slide, in this discussion, actually in this slide, actually we will only assume the quadratic representation for cost function. Okay. That's why I may say in the problem statement of complex engineering problem that you have to take the any representation of cost function rather than this quadratic function. Okay. You can take this quadratic representation, otherwise you can take the other. Okay. So you will do the literature review, then you will choose one for you. Okay. So that will be your first step. Obviously there will be lots of steps remaining after that. That will you will know gradually. Okay. Whenever we will solve the economic load discuss problem. Now for this discussion, we will assume that our cost function is a quadratic representation. Okay. That means this is the CI. CI is the cost function. Obviously, it will be the function of PGI, right? If you increase the PG, obviously the cost will be increased, right? And why there is the indexing of I? Because let's say we have 10 generators, right? So this I will be from 1 up to 10, okay? And there will be 10 different cost functions for 10 different generators, okay? Let's say if I is 1, then it will be C1 of PG1. So the cost function of generator 1, that is C1, will be obviously dependent with PG1. It will not be related with PG2 or PG3, right? C1 will be dependent on PG1. C2 will be dependent on PG2, like this way. That's why this is CI and it is a function of PGI. Okay. That is the power generation from that particular unit. It will be alpha I plus beta I PGI plus gamma I PGI. Okay. This alpha, beta, and gamma. Okay. These are the fuel cost coefficients. Fuel cost coefficients. Let's say here also the indexing are here the I, right? That means if there are 10 generators, so for each of the generator there will be different alpha, beta, and gamma. Okay. And these values will be given in your problem, either using a table or directly it will be given. Okay. So now what is your only unknown parameter? That is the PGI, right? The power generation from the unit I. And depending on this PGI, you will get the cost CI. Okay. And the unit is dollar per hour because this is the fuel cost. Now from this fuel cost, can we find the incremental cost? You know that the incremental cost is nothing but the differentiation of fuel cost with respect to the generated power, right? That's why this is the differentiation of CI with respect to PGI, right? If you differentiate it, you will get this term will be vanished. Then here you will get the beta I, and for this square term you will get 2 here, 2 multiplied by gamma I PGI. Okay, and obviously the unit will be dollar per megawatt hour. Okay. Now by looking into this expression, you can see that whenever the PG is 0, still you are getting some cost, right? Can you say why we are getting some cost at PG equals to 0? Yeah, this is due to this preheating stress that actually we already discussed here, right? Because we saw that here there are some fuel cost at P equals to 0. Because at first we need to start up all the equipments, right, to generate the effective power from the generator. So any other question up to now? No, right? Now with this concept, let's solve one simple problem. Okay, so this is a very simple one. So for a 2 generator system means in our system we have only 2 generators. So these 2 are the fuel cost for these 2 generators. This is for generator 1, this is for generator 2. Obviously this C1 is the function of PG1, C2 is the function of PG2. Look, the alpha, beta, gamma values are given, right? These values will be given here. Or these values will be given in the table, like this. So this is alpha, beta, gamma. So this is the generator. Okay. Generator 1, generator 2. For generator your solution will be the Pg1, Pg2, right? The solution of ELD will be the Pg1, Pg2. And what will be the goal? Goal is to minimize the fuel cost, right? On the total fuel cost CT, that is the addition of C1 and C2, right? And to actually achieve this goal, you have to fulfill some constraint, like you have to meet the load demand, then you have to meet the generator limit constraints like this, okay? But finally you will get some solution for Pg1 and Pg2, okay? Then the addition of this Pg1 and Pg2 should be equal to the PD for the load demand, right? And also this Pg1 and Pg2 value should be under the minimum and the maximum limit for that particular generator, right? That is the case. So if you have the cost function, can you determine the incremental cost? You can simply differentiate it, right? So differentiate it with respect to look. This is IC1. It will be the function of Pg1, and you have to differentiate this C1 with respect to Pg1 only. Okay, you will not differentiate it with respect to Pg2. So then you will get the 20 plus 0.02 Pg1, and the unit will be dollar per megawatt hour. Similarly, you can calculate the incremental cost for generator to IC2. Now you are getting these two things. Now in the next slide, let's say we have solved the ELT and we have got these two information, that our Pg1 is 250 megawatt and Pg2 is 150 megawatt. Okay. Obviously, these two information will be come from the solution of ELT. Yet we haven't started the solution of ELT. In the future classes, we will see that how to solve the ELTs. Okay. Then actually we can find this information. But for the time being, let's assume that you have got these two information from the solution of ELT. Now, if you put these two values in your cost functions, okay, and the incremental cost functions, then you can get the exact amount of cost, fuel cost as well as the incremental cost. Okay. So put the Pg1 value in the first expression, then you will get the C1, then the C1, then the C2 will be this, right? And what will be the incremental cost? It will be this. Okay. Can you see this thing? And you have to actually write the unit correctly. It will be the dollar per hour. It is actually the dollar per megawatt hour. Okay. You understand this thing? Now, up to now we have discussed about the formulation of fuel cost and incremental cost. Now let's formulate the economic dispatch for the overall ELD problem. Okay. Obviously, this ELD is an optimization problem. So any kind of optimization problem is actually represented in this manner. Okay. There are two steps that I have already discussed in the first slide. First step is to define the objective function, and the second step is to define the constraints. So first we have to define the objective function. So what is the goal of economic load dispatch? The goal of economic load dispatch is to determine the generation dispatch that minimizes the instantaneous operating cost subject to the constraint that total generation should be equal to the load plus losses. Right? Here only we will consider the fuel cost as the operating cost. Okay. That's why what will be the objective function? It will be the summation of fuel cost. That is the total fuel cost CT. It will be the summation of all fuel cost. And this I will be from 1 to n. N means the number of available generators in our hand. And such that, so this is actually the constant.
So there will be an equal sign. CT equal to.
Yeah, actually this is actually equal. Yeah, CT equals to this. Then this is the constant, first constant, equilibrium constant. What is that? The summation of generation from all available generators should be equal to the load demand plus losses, right? Then we can add another constant like this, or PGI, or the generation from any particular unit I should be within this bound, PGI max and PGI obviously this thing, these values will be given within your problem. Okay, these values will be given. So after solving the ELT, you will check whether your solution set PG1 and PG2, if there are two generators, are within this bound, and whether this summation of these two are satisfying this thing. Okay, and for that solution, your fuel cost will be the minimum one. Okay, that will be the most optimal value or most optimal solution, or the optimized solution. That's why this type of problem is called the optimization problem. Okay, have you understood this thing? Let's say your demand is 400 megawatt. Okay, let's forget about the loss. Okay, let's just think about the load demand. And you have two generators, so you will have the PG1 and PG2. Okay, let's say there is some limit. PG1 mean actually the, let's say 100 megawatt. Okay, and PG2 mean, let's say 50 megawatt. Okay, PG1 max, let's say it is 350 megawatt. PG2 max, let's say it is 200 megawatt, right? So considering these constraints and this load demand, you have to generate the solution of these two, right? And also there will be some cost curve C1 and C2. So you have to keep in mind that the total cost should be minimized, right? Obviously, by looking into these things, you can see that, okay sir, we can take 300 from here and 100 from here, which will actually fulfill the load demand, as well as these two values are within this limit, right? But maybe this solution will give you the higher cost. Okay, maybe there are still some solution set which will give you the lower cost, as well as it will be under these limits. Okay, so that's why you need to solve the optimization problem. Okay, have you got the idea? So actually from the next class we will start this slide. We will go into the solution of ELT, and there will be few types. Okay, so in the first type we will go into the unconstrained optimization. Okay, so one thing actually I forgot to mention here. Sorry, here actually. So this is the optimization problem steps, right? If we neglect or if we ignore the constraint part, then that will be our unconstrained optimization. Okay, whenever we will consider the constraints, that will be the constraint optimization. Okay, so there are two types of optimization: unconstrained and constrained. So in the first type, we will solve the unconstrained ELT, then we will go to the constrained ELT. And for the constrained ELT, in the first type, we will neglect the generator limits, also the losses. Okay. So initially we will ignore the generator limits and the losses, and we will solve the ELT. Then gradually we will add these things. And finally, the last type will be including all the constraints like generator limits, losses, all the things. Obviously that will be a bit complex. Okay. And we will solve the ELT here using some numerical technique. Okay. And these techniques are very much old technique. And these techniques are only useful if you solve for a small system, like your system has let's say 2, 3 or 5 generators like this. But if your system is big, like if you have 100 generators, 50 generators, which is very much common, right, in practical system, at that time this approach will not be used. Okay, so there are some modern techniques called optimization algorithms. Okay, you can search in the Google and you can see that there are lots of optimization algorithms published year by year. Okay, you can see some genetic algorithm, particle storm optimization. This type of algorithm are actually very much convenient to use in case of the bigger network. Okay, but in our hand calculation, we will see the small system. Maybe there will be only 2 or 3 generators, and we will solve those things using some numerical techniques. Okay, that will be the things. So that's all about our today's class. So in the next class we will start this topic. If you have any question you can ask.